Hello everyone. Now we are going to solve one very nice fundamental problem to study the radiation heat transfer. This problem is important because it gives you a clear idea about how to deal with various quantities which are associated with radiation heat transfer from a single surface. So the problem statement is in the description. There is an industrial furnace which can be considered as a black body. It is emitting the radiation at 2500 degrees Celsius temperature. We need to determine monochromatic emissive power, that is emissive power at a particular wavelength, and the wavelength for which emissive power will be maximum, as well as the magnitude of that maximum emissive power, then total emissive power, that is emissive power considering the furnace as a black body, and also the emissive power considering that, or assuming that the furnace is not a black surface but it is a real surface and it has certain emissivity and it is equal to zero point 0.9. So you can see there are five different scenarios or five different parameters or quantities that we need to evaluate in this problem. So let us proceed with its solution. First of all, we will systematically write down whatever is given to us. So which are the given quantities? So the quantities which are given to us, the foremost quantity is temperature of the furnace and it is equal to 2500 degree Celsius. Now the most important care that we should take while dealing with the radiation problems, and the point at which students make the most of the mistakes, is that they do not convert the given temperatures into Kelvin scale, which is utterly wrong. So firstly, we will convert this 2500 degrees Celsius into Kelvin by adding 273 into it. So we get effective operating temperature of the furnace as 2773 Kelvin. Then there is one more thing which has been given to us. It is, firstly we need to find out the radiation, monochromatic radiation at a particular wavelength of 1.2 micrometers. So we will convert it into proper system of units. So it will be 1.2 into 10 raised to minus 6 meters. Also, for one particular case, emissivity has been mentioned as zero point 0.9. So these are our given quantities. So now there are five unknown parameters that we need to find out. So we will now proceed towards the solution. Okay, so the first parameter, the monochromatic emissive power at 1.2 micrometer wavelength, which means we are supposed to find out the emissive power at a particular wavelength. So we are supposed to find out EB lambda. So we can determine this using Planck's distribution law, which tells us that EB lambda is equal to C1 into lambda raised to minus 5 divided by, in a bracket, exponential of this entire ratio, that is C2 by lambda t exponential complete minus 1, entire exponential quantity minus 1. Now in this case we already know the values of C1 and C2. So C1 is given as 3.742 into 10 raised to 8 watt into micrometer raised to the power 4 per meter square. But then again, the system of units is inconsistent in this zone. We have to convert this micrometer into meter, and we know that 1 micrometer is nothing but 10 raised to minus 6 meter. Same thing we have done over here as well. So we will repeat this exercise, so that will give us 3.742 into 10 raised to 8 as it is, multiplied by converting this micrometer as 10 raised to minus 6, and still its power will be 4. So watt per meter raised to 4 per meter square. Alright, so here we can easily figure out that this will be minus 6 into 4, this will be minus 24. So 3.742 into 10 raised to positive 8 multiplied by 10 raised to minus 24 watt into meter raised to 4 per meter square. So it will be, so this is 10 raised to minus 24, this is 10 raised to positive 8, so that gives you 10 raised to positive 16. So we can get this easily as 3.742 multiplied by 10 raised to minus 16 watt into meter raised to 4 per meter square. That's the value of C1 that we have obtained. Now we should be focused on the next value of the next constant, that is the value of C2. So we have the value of C2 from Planck's law, that C2 is equal to 1.438 or 1.439, you can say 1.438 into 10 raised to minus 2 meter Kelvin. This value is already available to you. Now we can substitute both of these values in the expression of EB lambda. I will keep my calci handy with me. So we will substitute value of C1 as well as value of C2. Okay, so what do we get at that point? We get EB lambda, the blackbody emissive power at a particular wavelength. C1 is 3.742 into 10 raised to minus 16 lambda raised to minus 5. Remember, lambda is 1.2 into 10 raised to minus 6 meter. This we have already figured out, so that's why now we can write 1.2 into 10 raised to minus 6 entire bracket raised to minus 5. Okay, so this is our numerator. Then it will need the denominator. It will be exponential of C2, that is 1.438 into 10 raised to minus 2 divided by lambda, that is 1.2 into 10 raised to minus 6 into T. T is 2773 Kelvin. So the exponential term is completed. This entire exponential term minus 1, whatever will be that outcome. So now we will start evaluating this answer. Okay, so we have our calci at hand. What we will do to simplify this, we will first solve the numerator, then we will solve the denominator. So this will be 3.742 into 10 raised to minus 16 multiplied by 1.2 into 10 raised to minus 6 entire bracket raised to minus 5. So that is 1.5038 into 10 raised to 14. That's our numerator. You can also do that directly in your calci, but I am doing that just to make sure that there is no mistake from the side of the students, and you have one step to verify your answer. So 1.5038 into 10 raised to 14, that is your numerator. Now we will find out the denominator. So we will proceed like this. So exponential of C2, 1.438 into 10 raised to minus 2 divided by, remember it is exponential of entire quantity C2 upon lambda T. So 1.2 into 10 raised to minus 6 into 2773. Now I have closed the bracket of denominator, and now I am closing the bracket of entire exponential, this parameter minus 1. So that will be 74.29. Okay, so now we have numerator, we have denominator. We can simply calculate EB lambda, 1.5038 into 10 raised to 14 divided by 74.29. So we have our answer 2.02 into 10 raised to 12. So 2.02 into 10 raised to 12 watt per meter square will be monochromatic blackbody emissive power at a wavelength of 1.2 micrometer. So that is our first answer. Okay, So now we will proceed with the next answer. The next parameter which has been asked is the wavelength for which the emissive power is maximum. So this answer we can obtain with the help of Wien's displacement law. So how do we proceed with that? So for Wien's displacement law, I will simply first write down the title. So according to Wien's displacement law, the relation between wavelength for maximum emissive power and the temperature at which it occurs is given as lambda max into T is equal to 2898 micrometer Kelvin. Okay, now in this case lambda max is the unknown quantity, temperature of the furnace is known to us, and right side is also known to us. So it gives us, so lambda max multiplied by 2773 is equal to 2898 micrometer Kelvin. Ultimately we can solve this. So at this point lambda max will be, I will directly solve it for you, 2898 divided by 2773, so that will be 1.045. so this is 1.045 micrometer. This is the wavelength at which emissive power will be maximum. Now the question comes, okay, emissive power will be maximum, but how much it will be? And we can actually prove it, that if you want emissive power, you can no need to prove, actually you can simply substitute that value in the expression of Planck's law at this point. You can substitute everything else you already know about C1 and C2. Instead of lambda, you can only substitute the value of 1.045 micrometer, and then you can get the relevant answer. But then again, this will be a tremendous calculation that you have seen in this term. So we can do that. We have a very simple term which is available with us for this purpose. So we can write it in some other form. So we can write the maximum emissive power okay, so this will be EB max, we can say, and this will be for lambda max, and we can simply write it with the help of one derivation that is not there in so many books. We can directly write it as 1.285 into 10 raised to minus 5 multiplied by the temperature raised to 5. So we will now directly substitute the values. You can use this formula in examinations also. This is from the reference book of R.K. Rajput sir. So this is 1.285 into 10 raised to minus 5 into 2773 raised to the power 5. So now we will solve this. So we will put down the value 1.285 into 10 raised to minus 5 into 2773 raised to 5, 2.10 into 10 raised to 12. So that will be 2.10 into 10 raised to 12 watt per meter square will be the magnitude of maximum emissive power, when actually we should say it will be at lambda is equal to 1.045 micrometer. That will be the maximum emissive power when the temperature is 2773 Kelvin. Actually we can also tally this answer, that in this case the emissive power at 1.2 micrometer was 2.02 into 10 raised to 12, while it is now 2.10 into 10 raised to 12. So this emissive power is definitely higher. Now we need to move on to the next parameter. Now there is the fourth parameter. the total emissive power if that furnace is behaving like a black body. So remember, if it is behaving like a black body, then total emissive power, which means emissive power across all the wavelengths of the spectrum, it will be simply the black body emissive power, and it is given as sigma T raised to 4, and unit of this will be watt per meter squared. So we already know the value of sigma 5.67 into 10 raised to minus 8 multiplied by 2773 raised to the power 4. So let us calculate this. So 5.67, my mistake, 5.67 into 10 raised to minus 8 into 2773 raised to 4. So that is 3352606. I will write it, then we will convert it into appropriate form. 3352606.15 watt per meter square. In a convenient form, we can write it like this: 3.352 into 10 raised to 6 watt per meter square. That will be some more convenient form. Also, accordingly, you know how to write it in kilowatt per meter square form, or you can also write it in megawatt per meter square form if there is demand for such an answer form. All right, so and the next and the last parameter that we need to calculate is emissive power, the total emissive power actually, if emissivity is 0.9. So simply what we will do in this case, the emissive power of a real surface, because now furnace is behaving like a real body, a real surface, so it will be epsilon into EB. So that will be 0.9 multiplied by the value of EB is already known to us. It will be, or actually we should also write it, epsilon sigma T raised to 4, one and the same thing. So 0.9 into 3.352 into 10 raised to 6. So it will be, we will just write it down. So 0.9 into 3.352, 3.0168. So the answer is 3.0168 into 10 raised to 6 watt per meter square will be the emissive power of that furnace if it is behaving like a real surface having emissivity of 0.9. So let me just recapitulate in a minute. So firstly, we took the temperature of the furnace, converted to Kelvin scale. We took the wavelength, converted into meter properly. Afterwards, we applied Planck's distribution law so that we can determine monochromatic emissive power, that is black body emissive power at a particular wavelength lambda. So in this case, C1 and C2, they are known parameters, but still their appropriate conversion is necessary. Then we substituted the value of C1, C2 and the value of lambda, and after manipulation, after this mathematical treatment, what we obtained was the EB lambda, black body emissive power for a particular wavelength or monochromatic. And then we wanted to find out the wavelength for which the radiation will be maximum, and it is given only by Wien's displacement law. There is a relation between wavelength for the maximum radiation or maximum emissive power. So it is lambda max into T is 2898. After substituting the temperature, we got lambda max as 1.045. But this is only the wavelength at which emission will be maximum, but how much it will be? It will be given by this formula, 1.285 into 10 raised to minus 5 into T raised to 5. So ultimately EB max, maximum emissive power, will be 2.10 into 10 raised to 12 watt per meter square. How do we know that this is the correct answer? Because there is a check available over here. This value is lower than this maximum value, so we have the answer with us. And And then we evaluated total emissive power, which is nothing but simple blackbody emissive power across all wavelengths using Stephen Boltzmann's law. So it is sigma into T raised to 4. If the furnace is behaving like a black body, it has emissivity equal to 1. So we get EB is equal to 3.352 into 10 raised to 6. If that furnace is behaving like a real surface and it has some emissivity equal to zero point 0.9, then at that point the emissive power of the furnace slightly reduces. It becomes 3.01 into 10 raised to 6. So I hope this comprehensive numerical, which covers 5 parameters in its analysis, is useful for you. Thank you.